Now we're going to talk about electric potential. Definition is pretty straightforward. Electric potential, using letter V, is defined as electric potential energy divided by Q. Often it can be referred to simply as the potential. Q in this expression is very similar to idea of a test charge when we were discussing electric field. Now, units volts. You refer to this like batteries, for batteries. It's in honor of Alexandra Volta. He did lots of work on electricity. And obviously, 1 volt is equal 1 joule over 1 coulomb. How you can see that? Energy is measured in joules divided by coulomb for charge. Just simply from definition. Also energy, we know that energy is work, and work is force that measured in Newton and times distance that measured in meters. So it's newtons over meters divided by coulomb. We also can use now electric fields to define electric fields and find units for electric fields. We can use volts. So electric fields can be measured in volts over meters. That is the same as Newton over Coulomb. To understand what electric potential is, we're going to look at the simple example. This is old-fashioned TV tube. And here is TV screen over here. And just use small pencil here. Here we can see charge plates, negative and positive. And U positive test charge goes over here, and it's accelerating along electric field lines in this direction. So then it hits the screen and we see the image. Well, in fact, actually in TVs they were not positive charges but negative charges. So for that we have to reverse potential, reverse electric field lines. So low potential is here, so negative lines here. We had positive here and positive here. So electric field lines and go from positive to negative this way. That means electron accelerating this way. And then it hits TV screen. Let's go to the next slide. What assumptions we're making here and what is our setup is we assumed positive test charge. We assume that we know electric field that has magnitude of E and the distance between plates is L. So charges travel distance L and electric field accelerates it. Electric force on the test charge is then given by Q times E, and the charge moves distance L, and the work done by on the test charge by electric field then is negative QEL. There is a potential difference between the plates, potential at the one plate and another plate, and we have to divide change in electric potential energy by Q. We just found it, change in electric potential energy, so hence dividing it by Q, we're just getting that potential difference between the plates is equal electric field multiplied by distance L. In actual TV setup, electron was used, not a positively charged particle. So to accelerate electron in the same direction, we need simply reverse direction of the electric field. Assume the electron initial velocity is 0, and we can apply conservation of energy in this situation. We assume no friction and no energy being lost. So that means that kinetic energy initial plus potential energy initial equal kinetic energy final plus potential electric energy final. And kinetic energy final is equal change in electric potential energy. Don't forget, we assume that this is 0. So in terms of potential, then we have to find velocity, the speed of electron. We would simply plug in expression, this one, over here and use that kinetic energy is mv squared over 2. So simple algebra, let's write it down. Mv squared over 2 is equal negative, positive, negative, negative, double negative, positive, E delta V. And so we're multiplying it by 2. Just do this y. Multiply by 2, divide by m, both sides of equation, and then take radical. We're going to get expression for final velocity. In some different situation, electric field may not be constant. It might actually vary with the position. And what's happened in this case? We can also understand it this way, that the magnitude and direction of the electric field related to how electric potential changes with position. Mathematically, we just wrote down that delta V is equal negative E delta X. Rearranging this term, just dividing by delta X, we can write down that the electric field is equal negative change in potential over distance. So, electric field is proportional to the rate of change V with position. Quite often, physicists use different units of energy when dealing with electrons and with electrons traveling somewhere. It's called electron volt units. And if you remember, we defined potential as potential energy divided by charge. Electric potential energy. That means electric potential energy is equal electric potential times charge. In units, we have volts multiplied by Coulomb equal joules, right? But instead of coulombs, we can just use one electron, and instead of joules, we would have electron volt is equal 1 electron times 1 volt. And this is now units of energy. Conversion between those two units, between joules and electron volts, becomes this factor. 1 electron volts is equal, basically, electron charge 1.6 10 to negative 19 joules. In a similar way how we dealt with electric potential energy, we can look at the electric potential due to a point charge. Again, it's too long to derive it. We need to use calculus in order to properly derive that what it is. But it is actually given by K times Q over R. And if you're looking graphically on it, it's just 1 over R function multiplied by KQ. And it's positive for positive charge, and it's below R, so it's negative when charge is negative. Since changes in potential or potential energy are important, a reference point must be defined, as always. The standard convention to choose that at infinity, electric potential is 0. However, in some problems, we take in electric potential 0 at the Earth. And this is how we can define electric ground. That the ground everywhere is where potential is 0. What's happening with electric field and electric potential near a metal? We already discussed what's happening with electric field. Let's just review it before we go to potential. Given solid metal sphere, it's in this picture, and with a positive charge Q. As metal sphere is a conductor, it means all extra charge resides on the surface and electric field inside is 0. The field outside any spherical ball of charge is given by simple KQ over R squared. So we treat it as a simple charge. So inside the sphere we have zeros, and we have a jump discontinuity to the values KQ over R squared, and then it spells out as 1 over R squared. Electric potential near metal is a little bit different. outside the sphere, it spells out as k q over r. Just to compare, electric field was dying out as k q over r squared, so dependencies doesn't die out as fast. However, inside the sphere, it keeps at a constant value that is equal exactly outside the sphere. So you just have to kind of realize that potential is constant inside the metal and electric field is zero inside the metal. And again, the potential at all locations in the metal sphere must be equal to the potential at the outer edge of a sphere. And everywhere inside a metal sphere, potential is equal kq over radius of a sphere. Quick summary. We know that excess charge in the metal in equilibrium always resides on the surface. And now we also know that electric potential is constant inside the sphere, inside the conductor. And what else important, that electric field lines approach perpendicular to the surface of metal sphere of any conductor. So if you have like any shape, electric field lines going either this way, perpendicular, or this way, depending on the charge. And that's true for any wiggly surface. It's always going to be perpendicular, 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 perpendicular at every point. Directions at either in or out, depending on the, is it plus here or minus here. That's the end of this video.